plan is to be quite elementary. I do apologize if I end up being too elementary. And then the second part of the talk is not going to be nearly as elementary. So let's start with the first couple words in the title, diagonalizing matrices. And let's remind ourselves about fact in linear algebra. I should also say my handwriting is generally considered subpar. So if you can't read something or can't hear something, please interrupt either just by calling out or in the chat. I'll try to keep track. And the same holds for any kind of question, of course. So here's a well-known fact from linear algebra. Suppose A is some square matrix with coefficients in a field. So could be the real or complex numbers or whatever field is your favorite. Such that A is equal to its own square. So such a matrix is called idempotent. Then A is diagonalizable. And in fact, it will be conjugate to a block matrix of the following form. There's going to be an identity matrix, an R by R identity matrix, where R is the rank of A, and everything else is going to be 0. And what I want to explain today is that this fact can be interpreted geometrically as saying that a vector bundle on a point is always trivial. So we'll see how we get there. First, I'll remind you how we prove this. And again, I apologize, it's very elementary, but bear with me because we'll see in the proof which parts rely on the fact that the coefficients of the matrix, the entries, are in the field F, and which parts do not. So there are 2 steps, and one of them relies on that being a field. That's the second one, but the first one does not. So suppose you have any vector v in F to the n. Then, of course, it is true that AV can be written as the sum of V plus the identity matrix minus A times V. Okay, that's clear. And so this implies that we can write A minus the identity matrix. That's the identity matrix. So we can write V as a sum of 2 vectors, namely A times V plus, and now the sign gets turned around, identity minus A times V. And then we note that A times AV, well, that's A squared V, but A squared is equal to V. So this is A times V. And if we multiply the identity matrix minus AV with A, we get A minus A squared times V, but A is equal to A squared, so this is going to be 0. So in other words, we have in fact written the vector V as a sum of 2 eigenvectors, or possibly the 0 vector, but 2 elements of eigenspaces. So thus, we have expressed our vector space Fn as a direct sum of the eigenspace with eigenvalue 1 and the eigenspace with eigenvalue 0. So these are going to be eigenspaces. And now if we are just doing first-year linear algebra, or any linear algebra as long as the coefficients are in the field, we are now done, right? Because being diagonalizable means precisely that every vector in the vector space can be written as a sum of eigenvectors. But there's something hidden here that we just take for granted in linear algebra because we can do row reduction or Gauss-Jordan algorithm. So now comes into play that F is a field, because F is a field. The eigenspaces E0 and E1 have a basis. Because every vector space has a basis. And their union is a basis for the original vector space Fn. And now we really have proved, that is, A is diagonal if we express it with respect to that basis. To this basis consisting of eigenvectors. Okay, very easy, nice. That all brought us back to undergraduate mathematics. So, as I said, there are 2 steps to this proof. The first step only needs it really only needs that matrix addition and multiplication are actually well-defined operations. So that matrix algebra makes sense. So we do need to add the entries in the matrix. We need to be able to multiply them. We need to be able to add them. And multiplication needs to be associative, and addition associative, commutative, and the whole thing needs to be distributive. That's really all we need. But in the second part, we need to be able really to row reduce, and that comes down to the fact that we can divide by non-zero elements in the field. We'll see that this is not a necessary condition, but it's certainly used in this proof. Okay, so that's nice. What about if we are only in a situation where we can add or multiply the entries in the matrix, but we can't row reduce? Is it still true that an idempotent matrix, A, a matrix that's equal to its square, is necessarily diagonalizable? And I will explain to you using 3 examples that this is not the case. Okay, so the first example is labeled Möbius strip because it's related to the Möbius strip, as we're going to see. So in this case, the matrix is a matrix of functions. So here, the coefficients of the matrix, so the little entries in it, are in, they're continuous functions, and they're continuous functions on the unit circle. And I want to express them using the usual parametrization of the unit circle. So I take continuous functions from the interval 0 to pi to the real numbers, such that f of 0 equals f of 2 pi. Okay. Those can be considered functions on the circle. I want all my functions to be continuous, as the sine and cosine functions certainly. So now you can compute. This is an easy homework exercise. So because sine squared plus cosine squared equals 1, no matter what you put into the sine and the cosine function, we see that a squared equals a. Okay, so this is an idempotent matrix, and the coefficients of this matrix are now not scalars, they're not just numbers, they're functions. And we can ask the question, is A diagonalizable? And of course, I wouldn't give you the example if the answer was yes. The answer is in fact no, but why is it no? Answer, no. So indeed, why is it no? Let's consider P. And P is called P because later it will be revealed to be a projective module over this ring of functions on the circle. So P is going to be all the continuous functions from 0 to pi to the real numbers. But now, instead of f of 0 being equal to f of 2 pi, I'm going to require that f of 0 is the negative of f of 2 pi. So this is a module over these functions. So this means if I take a function in P and I multiply it with the function on the circle, I get another function in P. That's clearly the case. And this operation, because it's given by multiplication of functions, satisfies all the usual associativity and distributivity properties that we need for a module. And one can see easily, it's not very hard, that P is in fact, well, isomorphic. And if you're not an algebraist and you're not happy with the word isomorphic, you can just, it identifies one-to-one with it. Isomorphic to what happens if you take just vectors with two entries being functions on the circle and you apply the matrix A. So it's what you might call the image or range. I guess range is not really correct, the image of A. Of A. So if A is diagonalizable, if A was diagonalizable, well, then the image of this thing would have to have a basis, and it's very easy to see that A is not one-to-one or it's not injective. So the rank of this matrix at some generic value theta, where the sine or cosine function are not zero, they're not both going to be zero at the same point, so it's not a problem. The rank is going to be 1. So if A was diagonalizable, then this image would have a basis. So that means then there must be a function f in P such that P is simply gotten by taking functions on the circle and multiplying them with f. But then if you think a minute, well, this can only be true if the function f is non-zero for all x between 0 and 2 pi. Because if it vanishes somewhere, then if you multiply it with some other function, it will vanish there. But it's clearly the case that there are functions on the circle that don't vanish anywhere. For example, the constant function is value 1, right? So this function would have to be non-zero everywhere. But now, see, we have that f of 0 is negative f of 2 pi. So either f of 0 is 0, or the sign of the value of the function differs between 0 and 2 pi. And that means it must have a 0 in between by the intermediate value theorem. So this contradicts the intermediate value theorem. So A is not diagonalizable. As I asserted here. Right, so we have actually done some algebraic K-theory, very elementary algebraic K-theory, just using a tiny bit of linear algebra and a tiny bit of first semester calculus. And I should say that I adapted this example. It's of course an extremely well-known example, but I adapted it from Y.T. Lamb's lectures on rings and modules, or modules and rings. Modules and rings. It's a beautiful textbook. There's an example in there that is closely related to this. Okay, now what does this have to do with the Möbius strip? Well, it has to do with the Möbius strip because we can also consider geometric interpretation. Geometric interpretation is that P is the module of continuous sections of the, well, not quite the Möbius strip, if you will, infinitely extended Möbius strip. So usually when we have the Möbius strip like here, we take the interval 0, 1, and then we glue it together like this, but just extend it infinitely in both directions. Infinitely extended. Möbius strip. Well, there's another word for this if you know topology. That is well, the Möbius strip infinitely extended is a line bundle over the circle, and this is the unique non-trivial line bundle. Non-trivial line bundle over the circle S1. And the fact that this matrix A is not diagonalizable, but it means precisely that this line bundle has no nowhere vanishing section, which precisely means that it is non-trivial. Okay. And so you could consider what we have done here, this little bit of calculus, as a proof that this is in fact a non-trivial line bundle. Right. Later, mostly in the second half of my talk, I will have to argue the other way around. I will have to find, well, not really vector bundles, just elements in some K-theory, prove that they're non-trivial, and use that to conclude that there must be idempotent matrices that are not diagonalizable. But for now, we're going in the forward direction. Okay, so that's one example. And I apologize for my bad picture. I've never been good at drawing, which is why I studied algebra, to be perfectly honest. Not so good with pictures. Okay. Example two. Example two will come from number theory. It will not come from topology. I'm giving this example because I want to show you that this whole question, are idempotent matrices diagonalizable, and the whole related big theory called algebraic K-theory actually shows up in many, many different areas of mathematics. So example two is from number theory. So here, I need to tell you where the coefficients are again. So here are the coefficients of the matrix. Of our matrix A are in the ring Z alpha, which sits inside the complex numbers, and it's just those complex numbers that can be written as an integer plus an integer times alpha, and alpha has the property that the square is -5. Okay, so it's just choose one of the two square roots of -5. So, and then you can write down this matrix. And if you just see this matrix, you are going to think, okay, how did you come up with this matrix? In fact, of course, it took me a long time to come up with it because I'm no longer good at basic algebra. But I will explain to you where it comes from. Now, it's again, this is a 2x2 matrix, and we have the relation that alpha squared equals -5. So you'll compute easily that a squared equals a. And I should say, this is of course provided that I didn't make an algebra mistake. So provided I did not make a mistake. I should say that for the story that I'm telling, it's not particularly important what the actual numbers in this matrix are, but I think I actually got it right. So this also is an idempotent matrix. Now, here the entries are not functions. They're just elements in this ring, and this ring has a name. This is the ring of algebraic integers. In the number field, in the imaginary quadratic number field, q square root -5. And if you have learned number theory, then you will now realize where I'm going. This is sort of the simplest number field you can find whose ring of integers is not a principal ideal domain. So that's what we are getting towards. Now, in this case, we again ask the question, is I diagonalizable? And now I have to be very careful what I mean. I mean over Z alpha. I can of course view the entries of the matrix as numbers in this field q square root -5, or even as complex numbers if I wish. And then linear algebra tells me the matrix is diagonalizable. But what I want to claim is it is not diagonalizable if all I'm allowed to do is change bases with a matrix whose coefficients themselves are these algebraic integers. So it in fact becomes diagonalizable as soon as you allow division by 2, which is also not incredibly hard to see. So the question is A diagonalizable over Z alpha? And again, the answer, otherwise it wouldn't be an interesting talk, the answer is no, it is not diagonalizable. And in this case, we again use the same type of argument as before. We identify the image of A with some module over these integers Z alpha and show that that module is not free. It doesn't have a basis. So indeed, if we send 2 in Z alpha to the vector 2, 1 minus alpha, and we send 1 plus alpha in Z alpha to the vector 1 plus alpha 3, then this identifies the ideal. So ideal being a subgroup of Z alpha that is sent into itself if you multiply with any element in Z alpha. So the ideal generated by 2 and 1 plus alpha, that's an ideal in Z alpha. And it identifies this with the image of A. So you just have to check that 2 and 1 plus alpha, which are 2 elements in this ring, they'll satisfy some relations. And you have to check that they satisfy the same relations as these 2 vectors. Please note that I'm not claiming that there's a function from Z alpha, from the whole of Z alpha to Z alpha squared. So this is going to be in Z alpha squared, which restricts to this. That's not true. Okay, so this identifies this ideal with the image of A. And now this ideal is not principal. This is a well-known fact. It's the first example of a non-principal ideal in a ring of integers. It's not a principal ideal. Cannot be generated by one element, which shows that the image of alpha, so of A times Z alpha squared, does not have a basis. Because again, it's very easy to see that the matrix A is rank 1. And that means, thus, A is not diagonalizable. Right, very good. So we see a pattern developing, right? The pattern is that, well, it is exactly what I emphasized when I gave the little proof from linear algebra at the beginning of this talk. The pattern is that the problem that can occur when we have an idempotent matrix whose entries are not just elements, scalars in some field, but maybe they're functions, or maybe they're algebraic integers, or maybe they're elements in some as of yet unknown ring. What can happen is that the image of this idempotent does not have a basis. Or it can happen that the kernel of the idempotent, the null space, does not have a basis. Either of those would be a problem. Okay, and now we're going to do one more example. Now this example is again a topological one, a geometric one, but it's subtly different from the first two examples in another way, which I will explain. So I'm claiming that this example is related to the tangent bundle of the two sphere. So here the coefficients are continuous functions on the two sphere. And I want to consider the two sphere as its usual, with its usual embedding. So it's going to be x, y, z in R3, such that the length is 1. So x squared plus y squared plus z squared equals 1. And if I do that, in particular, x, y, and z are functions on the two sphere, right? I just send a point on the two sphere to its x, y, or z coordinate. So this matrix does in fact have coefficients in this ring of continuous functions on the two sphere. And again, we compute a squared, and it is easy to see that a squared equals a. And that's because x squared plus y squared plus z squared equals 1. So you only have to compute a couple coefficients of a squared, basically by symmetry, right? There's not much going on. So a squared is in fact equal to a. And so we can again ask the question, is a diagonalizable? And again, the answer is no, it is not. But, and the but will be discussed in a minute. So it looks like exactly the first two examples that I gave, but it is in fact subtly different. So here I will not spend too much time talking about what exactly or explaining why A does what I will say in a second it does, but I'll just tell you. The image of A, so that means you take vectors with 3 entries, all of which are continuous functions on the 2-sphere, and you multiply that by A. This is isomorphic too, so you can identify it without loss of information. The module of continuous sections of the tangent bundle of the sphere. So, in other words, the module of vector fields on this continuous vector field. So it's a bit strange, but fine. Continuous vector fields on the sphere. Well, if A was diagonalizable, if it is diagonalizable, that would mean that the module of continuous vector fields has to have a basis. And whether that has rank 1 or rank 2, of course it has rank 2, but that's not so important. A basis element must be a nowhere vanishing vector field. So if A is diagonalizable, then there must be well, 2 linearly independent, but at least 1 nowhere vanishing vector fields on the sphere. Fields. On the sphere. Well, we know that this is not true. So this contradicts a basic result from algebraic topology, which in English is known as the Hairy-Ball theorem. In German, if you translate the German label for the theorem into English, it's known as the hedgehog theorem. So, well, we all know this. If you, we all have some little sources or sinks of sources, I should say, of hair on our head. You can't just comb it all the way around. Or if, to give another example, there's always at least 2, because the order characteristic of the sphere is 2. There's always at least 2 points on the surface of the Earth where the wind speed is 0. So again, this means this matrix A is not diagonalizable. Now here's another pretty bad picture, which is supposed to explain the but. So the matrix A is not diagonalizable, but if I make it a little bit larger, if I make a 4x4 matrix where I add a 1 in the lower right-hand corner or the upper left-hand corner, so this is a 4x4 matrix whose entries are also functions on the 2-sphere. This matrix is diagonalizable. And the reason can be found in this picture. The 2-sphere is embedded into 3-dimensional space, and the normal bundle is trivial because you can just always point outwards. So this additional 1 here is the normal bundle of this embedding. So if I take the sum of the tangent bundle of S2 and the normal bundle of S2, maybe I should call it nu, because I'll use n for something different later. Oops. The normal bundle. So the bundle consisting just of normal vectors at each point of the sphere of the standard embedding. Well, this direct sum is in fact just a trivial rank 3 vector bundle. There's 2 times R3. And that means that this bundle, which corresponds to this square matrix, and since A squared equals A, the square of this matrix is equal to itself as well. This is an item, this matrix, sorry, it's an idempotent matrix. I apologize, you can't see where I'm pointing, of course, you can only see what I'm writing. So this matrix is also idempotent. And its image are the sections. So this corresponds to sections of this bundle here. And since this bundle is trivial, those sections actually do admit a basis as a basis of functions on S2. Right. So this matrix A is not diagonalizable, but if I make it a bit larger, it becomes diagonalizable. And now I will give you a definition. Let R be a ring. So a ring could be something like the real or complex numbers, but it could also be continuous real or complex valued functions on some space. Or it could be your favorite non-commutative ring, like a matrix algebra or group ring, something like this. Or it could be the kind of commutative ring that appears in algebraic geometry, and that's what it's going to be in the second part of my talk. So let R be a ring. An idempotent matrix. A, which is some n by n, some square matrix, where n is just some natural number, with coefficients in R, is called stably diagonalizable. If the block matrix that has one block of A and one identity block of some size is diagonalizable for some S. For some natural number S. Okay. And of course, it's very easy to see if you think of how linear algebra works and how it would work even if you did linear algebra over the ring R as opposed to a field. Once one of these matrices is diagonalizable, if you make it even larger by adding more ones in the lower right-hand corner, it stays diagonalizable. So this is a perfectly fine definition. And now we can ask, in general, the following 2 questions. When are idempotent matrices over a ring R stably diagonalizable? And that's the question I will mostly address today. And the second question is, when are they unstably? So really just without adding anything, diagonalizable. Right. Any questions at this point? Sorry, I should have asked earlier. None? Okay. So I'll finish this first part of the talk by talking a little bit about K-theory. K-theory allows you to, in principle, answer question 1. Question 2 is, well, you can ask this question for a particular matrix, like we did in the 3 examples. And if you have a particular matrix, you might be in luck and it might not be so hard to answer either 1 or 2. And in fact, in some sense, it might be easier to answer 2 because to answer 1, you can't be sure how much of an identity matrix you have to add in. But if you want to answer such questions for all matrices with coefficients in R, then the answer to question 1 is provided by K-theory, whereas the answer to question 2 is much harder and works by applying methods from algebra, or indeed in modern times also maybe things like motivic homotopy theory to question 1. So reduction to question 1 is the way to go here. And so I will finish by defining the group K0 of ring R, which is typically called the Grothendieck group because it was introduced by Grothendieck. K0R is the following group. So a group is something where we can add and subtract elements. And that is much more useful than you might imagine if you want to study the question whether matrices are stably diagonalizable for all matrices simultaneously. So in the language that we have used so far, we take the set of idempotent matrices up to stable conjugation. To stable conjugacy. So we don't care about base changes. And I'll tell you how to add 2 of those. And then we multiply by Z, and that Z is supposed to give you the rank of the matrix. Since I'm using idempotent matrices up to stable conjugacy, they no longer have a well-defined rank. So I'm keeping track of the rank by an integer, which I allow to be negative. And what's the addition here? Addition is just block sum of matrices. So the equivalence class of a matrix A, idempotent matrix plus equivalence class of an idempotent matrix B is defined to be the idempotent matrix like this. And this is not a commutative operation, but stably it is a commutative operation because stably I'm allowed to switch the columns and rows around. So stably. This is commutative up to conjugacy, and so I get an actual abelian group. And of course, the 0 matrix, which is idempotent, is the 0 element in this group, commutative up to conjugacy. A0R is an abelian group. Jing, if I may have 2 more minutes, I will write down a couple examples that we have basically now seen of this group. If F is a field, then K0F is just the integers, because the only invariant of an idempotent matrix is its rank, since they're all, in fact, diagonalizable, not just stably diagonalizable. So that's easy. So this is linear algebra. We have already proved it. K0 of continuous functions on the circle. Well, it turns out that is Z mod 2 times Z. Z is the rank, and the Z mod 2, the non-trivial element, is the Möbius strip. If you take continuous functions on S2, well, this one is just Z again, which is a little bit disappointing if you think about it. That's because the K-theory cannot see the tangent bundle. From the point of view of K-theory, the tangent bundle is trivial because it is stably trivial. Jing, interrupt me if I'm miscalculating. I hope I was not miscalculating. And K0 of Z square root of -5, which is this ring of integers in this non-trivial number field. So this is just going to be Z times the ideal class group of Z square root -5. That's a general fact if you know what the ideal class group is of a Dedekind domain. K0 of the Dedekind domain is always this product. And in this particular case, this is also Z times Z mod 2. Okay, I think that's me with part number 1. Thank you.
Thank you. So let's thank Christian for the first part of the talk. Any questions?
I have one trivial vague question. So for idempotent matrix, I think for nilpotent, people study like a to the some any integer power equal to 0, right? For idempotent, is it possible to study like a to the n equal to a, or is it meaningless? I don't know.
Yeah, that's a good question. When I started my talk, I realized that that why not a to the n equals a, but the sort of the analog to nilpotent isn't really idempotent. It is unipotent, so some power of a is equal to the identity matrix, and there the power can be anything. But for certainly when you use K-theory, you really need a squared equal to a, because secretly, well, so this is, what if I had been a bit faster, I would have tried to explain. So let me just use the opportunity now. So an idempotent matrix over R. So since if a squared equals a, then the identity minus a squared is also the identity minus a is also idempotent. This is I minus a, because 2a squared is a, so we get I minus 2a plus a, which is I minus a. So this idempotent matrix decomposes Rn into 2 pieces, and those pieces are called projective R modules. So idempotent matrices up to conjugacy are basically the same as projective modules up to isomorphism. And then if you are in the geometric situation, or in the topological situation, those projective R modules, those correspond to vector bundles on some space X, if R is functions on X. And this can be, I'm being intentionally vague, because functions on X can be continuous functions, or they could be differentiable functions, or they could be holomorphic functions, if that makes sense for X. Or in the second part of this talk, there will be regular algebraic, so rational functions. So that's why this is what's related to K-theory. Now, since I only thought of this same question at the beginning of the talk, I didn't have time to think whether it's maybe just true that if a cubed is a, then a squared already had to be a. Well, maybe not. So, but that's a fair question. I don't think there's any sort of structured way of studying that. Unless it is the same question, which it may well be, we should all sit down and do our linear algebra, basic algebra. But if it is not the same question, I don't know of any structured way that it's being studied.
Okay, so we should probably take a break and save the question for after the second session. Okay. Thank you, Christian.
Right. Yeah, you're welcome. I'll see you in 8 minutes or in 3 minutes. When are we continuing?